I've got a bunch of questions for you, which I'd really like you to help answer, the ones that interest you. I don't think I've got any particular answers here. And I'm going to comment on some challenges and some opportunities, making no pretense to be comprehensive. And let's try and finish early so that we can have a discussion. Okay, so how do I advance slides? I can talk without slides if you want. Or shall I do them on there? Okay, so let's start with two facts. So fact number one, cardiovascular diseases, plural, are really important. You all know that. That's one of the reasons that you're in the room. Fact number two, there is a staggering growth of new data accessible to researchers. Vision. Health Data Research UK, which is the new national, if you like, the Data Science Institute for Health, has been established last year. Director Andrew Morrison has this rather muscular vision statement, which reads, every health and care interaction and research endeavour will be enhanced by access to large-scale data and advanced analytics. So no poverty of ambition there. What do we mean by large-scale data? So 65 million citizens in the United Kingdom, so towards national scale and towards ever greater detail about the characteristics of patients and underlying molecular and other mechanistically relevant information. So where are we now? And let me talk about some growth points. So UK is blessed with national disease and procedure registries brought together in NICOR. If you plus those by linking to national hospitalisation data, you've got national coverage and you're getting more information. That's why it goes horizontally there. Another example, clinical practice research data has dramatically expanded the number of primary care practices that it includes. That's the plus there that is actually online now in 2019. But what if we had a national primary care data set? So 65 million people do have a primary care record. So there are levers for that to happen, partly out of GDPR. Deep, detailed hospital data, so moving along to the right, more detailed data, the Health Informatics Collaborative sharing data across 5 hospitals, only 5 of the 150-ish hospitals in the UK. UK Biobank, which many of you will know about, some of you were funded to work on in this programme. The plus there as whole exome sequence data is added to that amongst other molecular phenotypes. And the only example here of something that could be called a learning health system would be Genomics England. So the 100,000 Genomes Project, which is now the plus here, is Matt Hancock's aspiration to have 5 million people in the UK with whole genome sequence data linked to their health records. That has return of results built in. It's an NHS transformation project. So the point here is its scale and detail, and in 2019 there are multiple new opportunities. Expect those to expand further. And I love this quote from Generation Genome, the Chief Medical Officer, on the genomics point, that we should even have to justify any research that does not include genomic analysis. That's a pretty bold statement. So, do we have today in the world one health system with these data together in a package? So, multimodal data, so text, images, values, imaging, genomics, biomarkers, and so on. I'm sort of tempted to get some audience participation here. Any ideas? Where would you say? Anywhere in the UK? At scale? No, definitely not. One example in the US, there are several in the US, but this is a really good example. So this is Vanderbilt. So here you have the different modalities as rows. You have the start of the addition of biological samples with DNA here in 2005 and the growth of those numbers and a number of data points here. So this is an example of where this can all come together in one health system. So let's go back to my two facts. So we've got cardiovascular disease is really important. We've got a lot of incident data. So a proposition is that cardiovascular diseases mainly are the unintended consequences of deliberate actions. So they're mainly our fault, right? So you are all one of these decision makers. You're maybe two of these decision makers, but certainly we're all patients and members of the public. So as a result of the things we do, I wonder if you took the stairs or went up the escalator as you came to the first floor to the Turing Institute, for example. Any healthcare professionals in the room? It's not a bad thing if there are. I think you're quite relevant. Good. Any guideline developers? I'm guessing not. I won't go through. Guideline developer. Excellent. Good. You're amongst friends here. And so on. So there's a bunch of different people, different organizations that make decisions. And those decisions, I think, importantly influence this fact here. And our challenge, I guess, is to take the instant data and refract it, if you like, to good value for those decision makers. And that's where the partnership with Turing and BHF comes in. So what's the big idea here? I don't know. Chris may have a different view. I'm not sure what the big idea, but one big idea is a big convergence of care and research. So one representation of this, which I think is quite useful, is the idea of the learning health system. Chuck Friedman and many other colleagues around the world, principally in the US initially, have had this idea of data to knowledge, knowledge to performance, performance to data, but with interventions changing this. There should be patient benefit at the center of this circle here. This isn't fundamentally a new idea, but it's the idea of the virtuous cycle, which I think is important as we give examples with different decision makers. So it's not data science full stop. It's not merely to understand the world. It's understand the world in order to change the world. So in Big Data at Heart, which is an innovative medicines initiative, European Union collaboration, there are many examples of these approaches that have previously been reviewed. So I'm not going to talk about any of those examples which are published. I'm going to talk about some challenges and some newer things. So where do we start? One, I think, reasonable place to start is with patients and the public as decision makers influencing their own health. So I could have taken that photograph in this building, but I didn't. We know that certain behaviors are really important for cardiovascular health and really, really tough to change. Okay? So we also know that we have always-on, rapidly proliferating methods of getting data about those behaviors. And we have some initial trial evidence that feedback loops may indeed change those behaviors. But it all gets pretty complex pretty quickly. How many's done direct-to-consumer genetic testing in this room? A small number. That will grow. In fact, our NHS is potentially going to offer that. And although that particular kit doesn't offer your genetic risk score for high blood pressure or BMI, you may well seek to have that information and decide on your salt intake on the basis of having a high genetic predicted risk of high blood pressure. 10 millimeter systolic difference between top and bottom quintile of those genetic risk scores. That's a huge difference, okay? And standing back, the idea of automated hovering, that we have 5,000 hours a year in which we're all awake, some maybe more than others, and can we, with these always-on technologies, influence a range of decisions at our individual level that might change health? Okay, healthcare professionals are extremely important here. There are 1.4 million of them in the UK, as you know. Here's a kind of current snapshot of some of the challenges. So maybe a hospital doctor makes 150 decisions a day, many of which are in evidence-poor areas. There are no trials, there's no sort of published evidence. Most of which, I think it's fair to say, are data-free. They're not learning from data that does exist, is curated, and is increasingly available in the national health system experience. And I think it's fair to say that doctors are still trained that it's in their brains or in published literature that answers, if they exist, lie. And I think you may have a view as to whether that's the right way going forward. So give you a really concrete example. So we all have circulating C-reactive protein and hemoglobin, and if one's high and the other one's low, both of those are risk factors, actually probably causally on causal pathways related to some cardiovascular diseases. What does the clinician do with that information if other causes have been ruled out? Ignore it? Say that they don't know? When the national system has seen thousands of these people beforehand. So why wouldn't a person or a physician say, I want to consult. I want to consult nationally, an informatics consult, patients like me at scale, and I want the result in clinical timescales in 48 hours. That's a whole bunch of challenges. Currently, we do not do that at all in this country. There are some early examples in the US. So potentially that idea of an informatics consult, if the patient wants to know what's going to happen to them with their high CRP and low hemoglobin, am I at high risk of developing an autoimmune disease, how often I should be monitored and so on. You know, you may want to build statistical models and make inferences about that using large-scale data. You may also want mechanistic models, computational biology and other approaches to get a best estimate of best treatments. What about situations where the doctors say they know, but actually the health system gives some indication that they may not be right? So one of the obvious challenges with genomic medicine is this idea of variants which are detected for reasons not related to the reason for the test, so-called incidental findings. I'll give you one example here. So these are variants. It's an example of variants related to arrhythmic cardiovascular disorders defined by different these are the variants defined by different laboratories as whether or not they're pathologic, clearly classified differently, and then followed up in real-world data in the health system. This is actually from Vanderbilt as well, as to whether they had phenotypic evidence of the arrhythmic disorder related to the genetic variants. It's a dog's dinner, okay? So what about guideline developers? Believe it or not, I think, guidelines are a really big industry, and they're really important, and they are mainly fish and chip paper. They're mainly ignored, I think is fair to say. That's a bit strong, actually. They're too often ignored or too often not adhered. That's a safer thing to say. So here's an example of a guideline. Most guidelines have this form that looks, if you don't read any of the print, that it might be computable. You've got something that's got a flow diagram, some logic attached to it. And I hope as soon as you do read the print, this happens to be the management of a common condition, heart failure, when you do read the print, you realize how uncomputable it is. Even if we could define in the health records what heart failure is, you can do that, and ejection fraction is, you can do that, but it's tough to do it at scale. You then have to then define some drugs. That's okay, you can define drugs, that's really definitely okay. But you've got words like offer, consider, if symptoms persist. Which systems? What do you mean by persist? Etc., etc. So to get this into a state where one could do data science with it, even if you use that as a starting point, and you may want to go earlier up the stream and do something differently, is tough. So is there a need in guidelines for some kind of change of product? Because there are, I don't think, please correct me if I'm wrong, these are human readable, but there are no examples of computable guidelines. Certainly for disease management, there are computable guidelines for very specific sort of value-based things. Not implementable in EHR. And even if you solve this or make this computable for one disease, guess what? Very, very few people shuffle off the mortal coil having experienced just one disease. Most people will experience simultaneously two or more. So trialists, how might trialists be using data? Just stand back, what do we need? I guess it's fair that we need more trials, we need more efficient trials, we probably need different kinds of trials. So here's an idea that comes out of Stanford, built around the clinical consultation, embedding trials in clinical care. the idea, clinical situation, is there a guideline available? I love it. Yes, just use it. So that's pretty simple. You may have views. Or let's say there isn't one. So bang, hit the green button, because by definition, the clinician is saying there's some kind of uncertainty, possibly equipoise about what to do. And then either, and this is the informatics consult idea, that you might interrogate large, possibly national data, and that may give you relevant, practice-based evidence, or you may route into queuing for new randomized trials. So I think that's an important set of propositions. To work through the data science of that has many challenges indeed. How am I doing for time? Okay. So I've got plenty of time, but I want plenty of time for questions. So drug developers. If you read whole swathes of learning health system literature, it's like drug developers are not part of the health system. Well, I think that's not helpful, actually, because drug developers, we need more drugs, we need better drugs, and we need to develop them more efficiently. Do you all know about Eroom's law? You know about Moore's law? Everybody knows Moore's law? So Eroom's law is the palindrome of Moore, and it says that the number of drugs, I should have had a slide on this, shouldn't I? Number of new drugs brought to market per $1 billion of investment is going to cost a big, it's just ridiculous. So we need efficiency. This is absolutely about decision making. If you're the R&D director at GSK or at AstraZeneca, and you decide to go to a phase 3 trial, which may cost $500,000 million, you want to be pretty clear that you're on the right thing. And we, I think, are pretty clear now that if one has genomic evidence of drug target validity, that is, which you can get much earlier than the phase 3 randomized trial stage, then that is associated with success in drug development. But we've got a bunch of challenges. So this is work from Arun Hingorani. So if we stand back and take a principled view of drug development and say, well, the targets for most drugs are proteins. Genes make proteins. Not all the proteins that genes make are druggable for various reasons. So 20,000 proteins, estimates of about 4,000 druggable part of the genome. And how many diseases are we talking about? You can count it in various different ways. This counts at about 3,000 diseases. That's not just cardiovascular diseases, that's all diseases. Why do we care about all diseases? Because guess what? Nature doesn't know that the British Heart Foundation exists and that hospitals send you to a cardiologist. Nature deeply does not know that. It's a bit like the old world of chromosome societies when people said, I'll work on chromosome 22 and you work on chromosome 21. Well, guess what? Biology is not organized like that. So anyway, I digress. So you've got the druggable genome, and so you've got, these as the sum total of target disease pairings. The proportion that have genetic, that have been explored in genetic studies is about an 80th, i.e. we don't have that many genome-wide association studies relevant for drug target validation. And appropriately, it's a lower number, but it's a way lower number, order of magnitude lower, is those that have been evaluated in randomized trials. So what's the upshot of this? The upshot of this is we need to massively expand our ability to do genomic associations in order to identify drug targets, if not for other reasons. So let me give you a very specific example of how one gets at drug targets through imaging. You're going to hear a wonderfully eloquent talk from Declan shortly, so I'm going to make some rather ignorant comments. Correct me if I'm wrong. So cardiovascular imaging at scale. So the image that is collected in 192 countries pretty much around the world in the millions and tens and hundreds of millions and then discarded is this one. So it's the ECG. So that's a digital signal which has beautiful physiology, beautiful genetics, beautiful human interpretability, because that's the R wave that gives you your heart rate, and even I can understand bits of it. And with signal processing at scale, so this is Pierre Lambiase, Pat Monroe and others' work in UK Biobank, you can carry out genome-wide association studies, as an example of it, and get lots of hits. This is a Manhattan plot. I guess you all know. Does everybody know that that's a Manhattan plot? Yeah, good. Everybody nodded. One person put their hand up. It's very good. So you really know what it means. Good, excellent. So above the line, these are associations that are likely not to be statistical noise with these different ECG parameters. So here, these are different heart rate parameters. Why does that matter? Well, it's maybe of interest to, well, firstly, your heart rate now, right, has clearly been shown at all ages, even from sort of college students, to be strongly related to a whole bunch of bad things later on. So higher heart rates on average, not good, including specific cardiovascular diseases. So what Pat Monroe and others did was to look at resting heart rate, which you've all got now. If you did run up those stairs, you would have a heart rate on exercise, and then after you sit here, you'd have a heart rate recovery. And you see that the genetic architecture of those two things is different, and interestingly, some of these hits in genes here actually are drug targets. For ivabradine, for example, the drug target is associated with HCN4. So new loci, new drug discovered for different heart rate phenotypes, which may be relevant for drug discovery. A further aspect that's relevant for drug discovery is, do we want to treat a case of this disease or that disease, or do we want to treat or prevent a case of disease progression or a severe case? And it's both, but our ability to focus on disease subtypes and trajectories, severe trajectories and so on, certainly in cardiovascular disease, has been modest. Here's a slide from Matt Nelson at GSK, which maps the number of associations with some sort of emerging trends as we go, yes, UK Biobank now, into Biobank consortia, routine sequencing and so on, into the subtypes and trajectories. So this point about emerging taxonomies of disease. Taxonomies of disease, I think, are important. They're not sort of stamp collecting, which some people might think they are. They're extremely important. So across rare and common diseases, how do we go from what we currently have, sort of bits of information in these different areas, to understanding how they come together to define treatment-relevant phenotypes or diseases? So I guess the process here is one which is central to many, if not most of those decision makers that I've mentioned too. It's not just for the drug developers. So if one says, first off, how do we define these diseases in multimodal data that have been collected oftentimes in the wild, in healthcare systems? How do we then subtype those phenotypes relevant for current clinical management? I gave you the example earlier of heart failure with and without impaired ejection fraction. And then how do we bring in discoveries of new subphenotypes based on causal understanding and that may be relevant to treatments? So to give you an idea of what sort of starting slopes of what might a new taxonomy look, or where we're starting from at least, is currently we have a really quite genuinely Victorian way of classifying all diseases, not just cardiovascular. So we essentially group them into things that are single gene disorders, nearly all of which are uncommon or rare. So there's about 200 of those which come under a cardiovascular, have cardiovascular manifestations, and about 385 diseases, with some overlap with the first slide, of statistical classification. So these are mutually exclusive. If you get into one of these categories, you can't be in another category, or you can't be, the relationships between the categories is not clear. So just, again, the idea of heart failure, I mean, that itself sounds Victorian, doesn't tell you what the cause is. So a challenge to this community, or this emerging community, is what can we do? What set of questions can we drill down on that might develop an atlas of a new atlas of cardiovascular diseases that might be relevant against etiologic criteria, against treatment, information, prognosis, or other things. That has not been done and could be done. Public health policymakers, how do we prevent a range of cardiovascular diseases? Public Health England is one of the important bodies here. It's not the only one. I shouldn't pick on them at all. There's a couple of things that one could consider. Currently, we agree to focus on the primary prevention of heart attack and stroke. We agree not to even do very much research on the primary prevention of more common cardiovascular disorders like atrial fibrillation and heart failure. Is that right? Is that wrong? We could discuss that, but I think that's a challenge. How do we approach multi-disease risk and screening? So we have GRAIL and circulating tumour DNA that may offer opportunities for early detection for a range of cancers. At the same time, that sample, do we also want to sample for lipidomics or other markers that may alter decision-making for the prevention of atherosclerotic cardiovascular diseases? What do patients want? Do they want a one-at-a-time screening, or do they want to essentially remain healthy? I suspect it's the latter. Even at a more basic level, public health has an important role to understand how cardiovascular diseases distribute in populations. So even if one asks a very simple question of over time, how do different cardiovascular phenotypes associate, I think we're at an early stage. So if we take the famous advantage of the NHS that offers cradle-to-grave care, it does, but we can look at cradle-to-grave records. So here, if you take, I'm going to go across the life course here. So these are some 300 of the most common diseases that are admitted or seen in primary care, and this is how they distribute. So this is the median age at diagnosis, and the reason I'm showing you this, this is between same diseases between age 0 and 40 years, and this is between age 60 and 80 years, and there's one cardiovascular disease, heart failure. The reason to show you this is, of course, the life course. A lot has happened by the time a patient appears in one study. And if one is interested in heart failure, all these diseases here are thought to be causally, probably, related to heart failure. Do we understand the sequence in which those occur prior to heart failure, how common that is, whether they have different prognosis afterwards, and so on? Again, these are early stage questions that might have useful answers. And I think we're going to hear some more about trajectories work with Marlis Hall's work. But to give you an example of the kind of approaches that have been applied to phenome sequencing, the temporal relationship between different phenotypic manifestations of disease. This is not from cardiovascular disease, it's from dementia. This is Danny Alexander's work, and I guess a question is, to what extent are these approaches applicable in cardiovascular diseases? So rather cheekily, the last decision maker to talk about is healthcare organisations. It's a bit cheeky because you could say, well, datasets, you could have put them first. Who spends the NHS's money? It's largely kind of healthcare organisations in a sense. What do we want data science to do for hospitals, for general practitioners, and so on? Well, there's a whole bunch of things. But I think there's an important question to ask is, do we want data science to do something really important, which is to create a faster horse? which is to get existing patterns of care and existing organisations' models of care to be more efficient. That's really important. Operations, when to see the next patient, scheduling and so on. Given some of the comments and possibilities I've made about the other 6 decision makers, what might data science do in terms of changing the structure and function of these organisations? I'll give you one example of that. Right now, you can't point at any hospital, I don't think any, in fact, I'm sure, you can't point to any hospital in the world that could tell you how good its care is. If you said, I just want to know how many of your patients adhered to current best clinical practice. There's not a hospital in the world can do that because, I just told you earlier, the guidelines things, there are hundreds of those guidelines. They're not computable. You wouldn't know the answer. Okay? I would say that answering a question like that with data science, probably not this year, but at some stage is probably important as we understand how to change these sort of bricks and mortars and social constructs which are important for healthcare. Okay, so last part of my talk, which is quite brief, which is, first part was a lot about the what, and now briefly something about the how. So I think the how, I hope that many of you are interested, well, I guess I do hope that many of you are interested in one or more of the things that I've said and interested in those decisions. And I guess the challenge is how do we refract these different kinds of data through the prism, if you like, of the people, the methods, the tools that Turing and BHF are bringing together. So I'll give you one example. So this is work, is Sebastian in the room? Sebastian Vollmer? I can't see him, so I'll assume he's not. Okay. So this is work that I think Sebastian has really done very well in bringing together with Turing, with NICE, and with HDR UK to put out 20 questions that one might wish to consider. No answers. This is not prescriptive, but 20 questions that are relevant in order to address some of the famous concerns of transparency, replicability, ethics, and effectiveness in machine learning and artificial intelligence. So I'm just going to highlight a couple of those. This is available in the public domain on bioRxiv if you want to check out the paper. Couple of points here. So first is the idea of data science in a vacuum as an ivory tower occupation. I think it has a role. I definitely think it has a role. Fundamental data science, I totally get that that's important. But I also think that the opportunity, and I think Chris mentioned this at the beginning, is that a good part of it is really embedded in systems, in healthcare systems, in health systems. So I wanted to highlight that one. I'm not going to mention the rest of these. I'm going to come back to this rather important. Are the different parts of the prediction modeling pipeline available to others? So this is a key part of the replicability piece. Evaluating impact, evaluating implementation. Okay, so here's a comment about replicability. So let's say we wanted to study one disease. Common thing to do, to focus on a disease. And at scale, the only show in town is to use electronic health records. And this is an example where the number of different algorithms just to define the disease that have been published in one disease, 76 different algorithms using the same underlying data, assessing severity A to control. So this happens to be asthma, but I suspect one might see a common thing in other in cardiovascular diseases. And clearly this is no basis for reproducibility and science. So how do we go from raw data here to something that's sort of human readable standard definitions of a disease state, trait or rate, as I say, pass it out into treatment relevant subtypes and allow discovery of new subtypes. So this is the effort of electronic health record phenotyping. I think the UK's got a real opportunity to make advance here. And by phenotyping, I think it's commonly three things together. So it's the code, which may be executable code, or it may be pseudocode, sort of human readable, or both, or it should be both, often both. It's the data at sources, is the code, and crucially, it's the set of often multiple validations that would give the relevant decision maker confidence in that phenotype. Again, just to give you one example, be a bit more specific about what I'm talking about. So heart failure, if you only have hospitalization data from NHS Digital, sounds like it might be quite simple because you've got these ICD codes, there's a small number of them, but believe me, different studies do different things, even with those small number. And then additional complexity in primary care and SNOMED codes, there's a whole bunch of different ones. So one has to make decisions about how to bring those together. So this is Spiros Danaxis's work in the Calibre portal, which is a UK phenome resources portal, which does have those components of the phenotype with the DOI attached to it and the metadata attached to it, the sources, as well as a whole bunch of validations. And that's public and open. The most important thing, of course, is you and your interactions. And here's an example of what I mean. So the people in this room working on one problem, I think, are relevant. I suspect that you could draw a roughly similar diagram of this room. The point is, I don't think there's two or three of any kind of one, two or three of any one kind of person here. So it's a multidisciplinary activity. Just to stay with the people piece, I do think healthcare professionals are relevant here. I do think that this slide is a problem. So there are 45,000+ hospital consultants in this country, and that's the number of those that are clinical academics. I would say that to make advance in cardiovascular data science, one has to bring healthcare professionals with us here. The Topol review made some helpful recommendations in this regard, but does not address these problems. And lastly, to wind up, as many of you will know, British Heart Foundation is seeking to establish a national cardiovascular data science centre, hub, name I think to be determined. Crucially, it's built out of partnership with data controllers, so NHS Digital, CPRD, Public Health England, amongst others. It will probably do some of the things that have been hard to do in individual centres, in individual investigator-led things that can only be done at a national level, so focus on expert services, training capacity, but I think should unleash the ingenuity and efforts of many in the room here. So, last slide, just by way of conclusion. This is a problem. It's our problem. It's the unintended consequence often of deliberate actions. I think we are making decisions here, but what you do, I'm guessing that many of you are both here and here. What you do here in refracting that data into something useful is really important. So thank you very much for your attention. Happy to have questions.